We will learn about how to design the roof trusses for steel structure or a residential structure in which the roof trusses are usually of steel. For design of steel truss for the roof, we will be using the example of a book. The name of the book is William Segui and is very popular for the design of steel structure. We will proceed to the design of the solved example provided in this book. The scenario is shown. We have fin trusses as shown in the figure spaced at 20 feet on centers with W6 by 12 purlins. We will start with Etabs and proceed with modeling of the structure. Selection of the design code and section database. AISC is the design code. We click on OK. The grids in X direction. In order to decide that, we see grid 1, grid 2, 3 and 4. We need 4 grid lines in X axis. And similarly for Y axis, let's say, since there is no limit here provided for the trusses, it's only mentioned that the trusses are placed at 20 feet center to center. Let's take 4 grids in Y as well. Since the spacing in X is 24, 42 and 24, so initially we'll take 24 feet and later we'll edit the center to 42 feet. Spacing of grid in Y is due to 20 feet on centers. Now for the number of stories, to define the top point, which is 12 feet from the bottom point, we'll take as a single story of 12 feet height, just for the reference grids. We click on OK. Once we have the grids ready, now we have to edit the grids. Display spacing under center grid spacing as 42 feet. Now we have the similar kind of scenario from spacing point of view in X direction. It shows a 0 to 12, so the height is 12 feet, which is exactly the required height. Now we'll start with adding the material property of A36, that is 30 ksi yield strength of steel material. Let's check the yield strength, which is given as 36,000 pound per square inch. Now considering the carefully geometry of the given truss, we see that we have purlins lying on the top chords and the bottom chord is between the supports. So we'll define with the frame sections. The only section sizes is given is as W6 by 12 for the purlins, that is wide flange section, while just for the exercise and design point of view, we will also design the whole truss. So we'll require to import the already provided section in the example and delete the other sections. While for the truss sections, we adopt usually the angles sections or the hollow tube, which are easy to form connections for trusses, as wide flange section does not form truss connections easily. So hollow tube, rectangular, circular can form easy connections for trusses. So from practical point of view, we'll select with the tube sections for rest of the truss, while the purlin sizes were already given as W6 by 12. Now for the rest of the truss, we'll go with square tube, starting with 4 inches tube size. Changing the material property to the given scenario, which was A36. Now considering the loads provided, we have superimposed dead loads of metal leg as 5 psf and built up group of 2 psf. So we'll add them in a singular load pattern, modifying the live load as a snow load, which are usually the alternatives of each other for inaccessible roof usually. Additional dead load, or we could have named it as super dead. Okay. So now, starting with the modeling part in Etabs, we'll proceed with modeling in the elevation window. Here we have rectangular sections. At each joint we are modeling them. Now the rest of the members, we need a snap on the midpoint of the structure. So we'll just draw a dummy line here, so that later on we can divide it into two, or just simply catch its midpoint for the center of the truss point. We'll go to the snap options and turn on the midpoints and endpoints option. So now you'll see we'll get a snap on the center of this line. Now we have no use of this line remaining, so we can simply delete it. So this is a perpendicular member and connecting to the Purlins line. So I suppose we would require to add the purlins first at a specific spacing that is provided. There are 8 spaces between the 9 purlins. So we gotta divide the line into 8 spaces. So we get 9 points where the purlins would lie. Remove these supports as there were no supports present here initially. So we got to model this member connecting the purlin point. I suppose this is the right point. No, this is wrong. Let's arrange the windows side by side so we can have a clear look at each instance of modeling. So now we have arranged the windows side by side that we have a clearer row. Okay, so I'm modeling the leftover frame. Assigning a roller support to this point is important for now, as we have to match the given scenario. So we have the points as well to match the purlins. It is important that we have broken the correct places the steel members, as it is very important for the steel structure model that you break the member at the correct location where you need to. We will simply replicate the frame to 4, as they were spaced at 30 or rather 20 feet center to center. So now we'll model the purlins joining the center or the visible points here, which we divided the top chord. So the 20 feet length purlins are being drawn here, connecting the fin trusses as mentioned in the problem statement. I'll simply draw these purlins between two trusses and just replicate them to the third and fourth truss, saving a lot of time. At the ridge point we have two trusses, you can notice, but here we have only a single point, so we need to deal with that as well in order to make the problem realistic. We'll take the offset from the center about 3 inches left and 3 inches right. The reason for selecting 3 inches distance is it is W6 by 12, so approximately its flange width would be 4 to 6 inches. So safely we can assume 3 inches on left, 3 inches on right for half of the flange distance. As we can see in the problem statement, the bottom flanges of the purlins are almost coinciding. So we need a 3 inch left and 3 inch right point. Let's take this as 3 inches. I suppose there's a bug here, that's the distance is not being fixed. Let's try. It's not getting the snap here. It's 21 feet line, but the distance I need is 3 inches, so I'm gonna delete these lines. By simply pressing the delete button. Where is the line? I really need it for 3 inches. I don't know why it's usually Etabs hold bugs for these kinds. cut the line, we got this point. Okay, so I'm gonna draw a straight line from there and again straight line from there and break the line at intersection of both of the lines. Now we can place the purlins over here. Similarly, we got to replicate these to the rest of the other trusses, or just simply delete those members. Either we can do it all together if we delete for all. So select the point to be replicated here and the frame parts, edit, replicate and apply. Steel structural modeling is a bit tricky, so you must carefully watch all my steps. The distance from the center of the ridge, I repeat, is 3 inch to left and 3 inch to right, for the reason it is a W6 beam and its flange width would be 6 to 4 inch. So for a factor of safety, we consider a flange width of 6 inch and we take 3 inches left and 3 inches right for enough space for the flange to accommodate, as shown in the problem statement for the ridge purlins. The purlins at ridge point, that is the top point of the truss, as highlighted in the figure on the left here. Okay, so I'm gonna need a dummy floor in order to distribute the load, the gravitational load. The floor must not have stiffness or its self weight, as we have manually accounted the self weight as metal deck for 2 psf. So I'm gonna add the property modifiers. You can take any material because we'll be ignoring the strength and stiffness of this slab or deck. So everything is negligible taken and reducing everything to the least it can be. Write Etabs automatically, even if it's calculating that point, so it's a very less load. So I'm gonna draw the slab between these already drawn purlins or the roof beams. It's gonna take a while. It would have been a lengthy procedure if I draw between each purlin. Rather, I'll select the purlins and then break the slab at the purlins. So it would be the same thing other way around. We can select the frame objects in a better. So now it has broken the slab to distribute the load between the purlins. That is a one-way situation here. Similarly for the other side, Etabs sometimes considered as floor or wall. So in order to select the shell objects, in order to assign the loads, I clicked on floor and walls. So now I'll be applying the uniformly distributed load to the shell elements, starting with the additional dead load. The metal deck is of 2 psf and build-up group is of 5 psf. So 2 plus 5 is 7 psf. Get a previous selection and apply these snow loads as 18 pound per square feet. Usually in Etabs we will take it as gravitational loads. It tells you that the snow load is horizontal and the other thing, that's okay. So yeah, (18 psf) of horizontal projection of the roof surface. It will be considering a lesser load for snow if I take as a horizontal projection. That means if I have a horizontal projection of 90 feet as shown in the figure on left, so I need to take the 90 feet by 20 feet as the tributary area for a typical interior truss, but conservatively I'll take this one as 18 pound per square feet as gravitational load. So it would be the other thing, same thing around. So I'm trying to select all the slab sections here, or basically the deck. I'm gonna replicate it to the other trusses center points. In a similar manner I've calculated the trusses. In order to check the loads, we can right click on them, edit shells, or just simply replicate command. We got replicate twice. Okay. Let's just now working on Etabs only, as we have done the initial modeling part, I suppose. So there are a few still things left in steel modeling. As I told you, steel modeling is very complicated for sometimes if you need or you don't have the idea where the connections might be. So if you notice, the top cords are still broken at the purlins, which is not the real case. So I need to join all the top cords. So I am deleting the rest of the purlins, or you may call it trusses. I'll do the modification in a single truss and then replicate them again. This could have been done in for earlier steps, but then I would not have gotten these points for joining the purlins, though that step was necessary. This is how steel modeling is done. So I'll select all the broken lines after I have used the points to join the purlins. Now I can join them. So it is now a single cord, which is exact thing that would be on the design. We can also shrink the toggle element so that we get to know where they are terminating. Since we know that the truss members always carry the axial forces, that is tension on compression, so we'll neglect or assign the moment releases at the truss end or the member joints, as the connection is designed such that the members does not carry flexure or moment, otherwise it will be a girder or other member. Typically truss is designed to carry only the axial loads. So now we have assigned the releases to the members. Now we'll try to delete the extra joints which were used for modeling. Okay, so there are no extra joints as these points depict the location of the purlins. I'm gonna replicate it again to the other points. It's gonna be 3. Okay. So now the modeling initially is completed, I'd say. But basically, since the purlins are connecting the truss members which are carrying the axial forces. You can also see the rendered view of the truss. Oh, we have missed a corner purlin on the extreme left. So that's how the rendered view is always useful to me. So yeah, it's a good option though. I usually prefer to use it most of the time. Now I gotta assign the end releases to these members as well, as I don't want the purlins to induce or transfer their negative moments to the trusses. I just want them to apply point loads on the trusses. You can make them as IMF, as usually I am not designing for seismic. In this we are using LRFD, load resistance factor design method. Overrides and other things. Make it as IMF, as we are not doing for seismic, at least in this video. However, in some places it is important to apply the wind load on the truss members here. I'll be loading the default combinations for AISC LRFD and add them in the design part. They are already added, while the rest two were deflection combinations, which you can always check by L by 240. That is permitted by the code. L by 240, that is span of the truss here is 90 feet, divided by 240 will give you the allowable deflection in feet. You can always multiply it by 12 to get it in inches, and check it on the combination that are service, live plus dead or so. Now basically we are done with initial modeling. Start with the analysis. So you see that we have to fix few things in the modeling, as it is an abnormal deformed shape. You can always check these by starting the animation or run animation just on dead loads. You can see that the top cord is not properly be connected to the ridge point of the truss, as unfortunately I might have missed joining the top cord to the last point, which was taken 3-inch left and 3-inch right in order to do the realistic modeling, to leave space for the flange of the purlin. It's actually not okay. So now the members are correctly joined. Let's check whether we have still assign the end releases to this point. I'll go and check, turn on the check for end releases. It is usually in frame members and end releases option. Okay, yes, we have assigned the member and releases. Let's run the analysis and then the design. First we'll check whether all joints are properly modeled. This joint is properly modeled, no disconnectivity or irregular deformation. Similarly with the other joints, they are properly connected. Turn off the horizon. I don't usually prefer to work with it. It confuses the lines. So the bottom chord is basically going under the largest deflection, which is, I suppose, reasonable. Okay, so now we'll proceed to the design part. Let's check the moment diagrams just for showing you that the trusses have very negligible or less moment, which is usually or most of the time due to the self weight only. As you can see, the load or the value of the maximum moment is only 1.8 kip fit. You might have come across in your experience the number of kip fit a flexi beam can take. That is 200-300 kip fit moment for a small size beam, while the moment we are getting and shear force is very low, which is reasonably due to its self weight. Okay, so let's go to deform and deform shape and start with the design of steel structure. Of course, there are much iterations in the design, so this is our first run. We'll revise the failing members and change some overrides. So you see there are a lot of failing members that are in red, but not all red color shows failing members. The black colored members are not designed. I'll show you the reason in the later part why they are not designed. So the stress is less than 1, demand or capacity ratio is less than 1, so it is okay, it is not failing. Not all red members are failing. It's just showing this demand over capacity is greater than 0.95, which we can always reduce to 1, so the members will most of the time pass. And then we can check, verify all members pass, 22 members are failing. So you can see the failing members here. It's 2.4 stress ratio, that is a high ratio, so we need a bigger cross section for the top chord, bottom chord and the bracings. Let's try to override the member sizes and see if they pass. Let's increase the thickness of the wall or the tube. Still it has reduced considerably, but not passing the check. I suppose it would have passed now. Yeah, so it's a 0.92 for the external truss, but for the internal truss, I'm sure the internal truss would be failing if I assign the same size to the internal truss, as the tributary width of internal truss is twice of the external truss for gravity loads. So in the next run I'm doing that. I'll unlock the model. And assign the largest passing member for the top and bottom chord. Usually these members are similar, as they are the primary frame of the truss, or the primary members for the exterior perimeter of the truss. From detailing and site execution perspective, it should be easy to execute. I'll have to delete the rest of the trusses and replicate that for a fast track approach. or the fastest approach to make sure I have to reselect them again. So delete. I'm going to replicate this with new assigned members that were passing, and I'm sure the internal truss would be failing at these members sizes, but just for demonstration purposes, you can see the purlins were not being designed as the design override is composite beam design. So we can select these W6x12 members and revise their design procedure to steel design and click on OK. So now it will also be designed, otherwise it would have been designed by clicking on composite beam option. But conservatively we are just here to design the steel frame. In order to make it more realistic, we can assign the unbraced length at particular points if the purlins would still be failing like they are. So we'll change the unbraced length factors. So still few of the members, or I'd say all the interior trusses, primary cords and the bottom cords are failing as I expected. So in order to keep uniformity, I'll keep the size of the external truss and the internal truss, top and bottom cord same. So I'll do some changes here. It should be IMF. I already did that, I suppose. Ignore seismic code for now. Yes. Ignore seismic load. Yes, we have already not defined it here. Consider deflection. No, which can only be checked manually, as I explained earlier in the part of the video, by L by 240. That is 90 feet of span. So I'll be adding few larger sections, larger from 4 inch by 4 inch. Let's go to 5 inch by 5 inch cross section for the tube. With an A992 property, I'll be using the 5 inch by 5 inch cross section. As I think increasing the material strength would help me. Don't worry about the book example, it was just to kickstart the real life problems. It was just to design the purlins. So of course we'll be designing the purlins in this video as well. So it's considered to be designed the same scenario. While these hollow shapes sections are selected by us own, they were not provided, so we can take the size according to the design output. So I have assigned the larger sections here on the periphery, top and bottom chord, that is 5 by 5 by 3 by 8, and I am gonna replicate it. Okay, so now we can run the analysis and then the design. So design is an iterative process. The proper the design, the better your project and understanding is. So the interior trusses are still being failed. So let's check the reason. It's pass as the ratio is less than 1. 0.96 is all okay, unless it's still less than 1. 40 frames have been failed. Let's check which frames. Show selected objects only. So the truss part that is failing is the interior cords, not top cords. I suppose they are not top cords. Yes, they are still hollow tubes of 4 inch by 4 inch section. so we must increase their size. Let's unlock the model. Although the exterior part is passing the check, but in order to keep the uniformity and ease of fabrication on site, and to avoid that mistake, for example, fabricator puts the interior truss on outside and exterior truss on inside, it's better to keep the things uniform and as simple as possible. So I'll be keeping the trusses similar. Is the choice of designer, whether in which country he is working, so all the things must be considered by the designer. It's not just the code but site execution and other things, as structure design is a very responsible job, I suppose. Okay, so we'll be replicating as similar in the previous steps. Made correction in the first on one elevation and replicated, so we don't have to repeat the correction for all. Again, designing. Now as I see the top chords of the center interior truss don't really cooperate here, but still they are economical design, they were passed, as Etabs did not select them as failing members. It only selected Purlins as failing members. So now it's time we incorporate the, as it was mentioned in the question, there is metal deck, so it would be diagonally bracing the purlins. Conservatively, we can take the bracing at quarter points of the purlins and assign the bracing, or we can reduce the unbraced length at quarter points of the total length of the purlin. So in order to do that, we have to show all the purlins first and then select them. So we will be selecting by frame property. Selected all the purlins, view, revise, overrides, or you can go to the lateral bracing and specify uniform bracing. Relative distance 3 points at 0.25 from the start, 0.5 and 0.75, as the end and start point is already braced. Okay. Additionally, if you want to assign the braces to the trusses by design overrides option, you can always select them and go to the view, revise, overrides, go to the unbraced length or LTB, minor and major. The reason for assigning in major as well is that there are chords and truss members coming, so they are bracing them in both directions. In major and minor. While the metal deck will only be providing the support or unbraced line reduction in the minor axis. So now all purlins have passed. You can see that we have passed the same size purlins as provided in the problem, with a 0.96 stress ratio of the center trusses. We have passed the center chords at 5 inch by 5 inch by 3 by 8 And please note that the truss span is 90 feet and the truss height is 12 feet. Let's try the detailing options of Etabs. I don't usually do steel drawings using Etabs. It's showing us the framing plan, deck and the purlins. Steel beam, schedule, material list, steel braces, material list. Yes, that's a good option in Etabs. It gives us the quantities. Wow. So apart from the main top chords, it's giving us the sizes of the members. Just the top chord is missing here. That's, I don't know, an error or something. Anyways, thank you for watching. Subscribe for more videos on the channel to come related to Etabs and other to come on structural engineering and related softwares. Thank you.